Hey, everybody. It's Wednesday, April 28th. And as you can see here in the aim today, our goal for today's video is all about discussing the concept of electrical resistance. Now, of course, in yesterday's video, the video on electrical current, I left you with a problem to solve on your own. And so the first thing I'd like to do in this video here today is to go over this problem. If you remember from yesterday, the problem said the current in a wire is 5.0 amperes, and there were two parts to this problem. The first part was to calculate the total amount of charge in coulombs that travels through the wire in 36 seconds. And the second part was to calculate the total number of electrons that travel through the wire in 36 seconds. So let's take a look at how you'd solve this. For the first part here, it said calculate the charge. And so we would say here for this part that the current was 5.0 amps. Of course, the time here is 36 seconds. And we were looking for the charge flowing in the circuit, and so that would be delta Q. Now, of course, the equation that we developed yesterday said I, the current, equals delta Q over T, the change in charge over time, or the amount of charge flowing over time. And so if we solve that for Q, or delta Q, we get here I, the current, times the time. Notice that that makes sense because even though we've written 5 amps as, in units of amps, that actually means 5 coulombs per second. And so if we multiply that by seconds, the seconds will cancel and we'll be left with the units of charge. And so we take our current here, which was 5.0 amps. We're going to multiply that by our time, 36 seconds. And when you do that math here, you get 5 times 36, which is 180 coulombs. So there's your answer to part A. The charge is the current times the time, which ends up giving you 180 coulombs. And that should make sense because, well, amps is measured in coulombs per second. When we take that times seconds, we get coulombs. Now, for the second part, it was not so straightforward, but it was still pretty basic based on what we said yesterday. I'm just going to write a separate list of knowns, even though you did not have to, just so you can really see the differences between how these two problems look when you get them separately. So, of course, they told us the current was 5 amps. And they told us the time was 36 seconds. And when you're solving for the number of electrons, you need the magnitude of the elementary charge, which is 1.60 times 10 to the negative 19 coulombs. And of course, here now, instead of looking for delta Q, we were looking for N. So the equation in the reference table says I equals delta Q over T, but the version of it that we need to use to solve this problem is I, the current, equals N times E over T, where N is the number of electrons, E is the elementary charge, and T is the time. And so if we solve that for N, we got to multiply both sides by T, so we get IT, and then we divide by E. So we get I times T over E. And now we can plug in those numbers here. Our current is 5.0 amps. Our time here is 36 seconds. So notice the numerator is going to be the same as the answer to part A. So that's going to be 180. But then we have to divide that by 1.60 times 10 to the negative 19 coulombs. And when you do that math, making sure you plug in all the numbers in parentheses, especially that denominator, because it's in scientific notation, you end up getting an answer of 1.125 times 10 to the 21 electrons. Now, that number is enormous. So notice, even for a measly 5 amp current, we get a huge number of electrons, 1.125 times 10 to the 21. Now, the last thing about this problem that I want to say is, if you solved this problem and thought this answer might have been wrong because you were thinking this is not an integer, I want to be very clear. This is an integer. This number is a 1, then a 1, 2, and a 5, and then it has 18 zeros at the end. That number is an integer. It just doesn't look like an integer when you write it in scientific notation because it has decimals. You have to remember, when that exponent is positive, you're moving that decimal point to the right. So you move it 1, 2, 3 times to the right, and then 18 more times. This number is an integer. Therefore, that charge is possible. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the main focus of today's video. Now, before we get into the concept of electrical resistance, I just want to make sure we're really seeing where all of this is going. As we said yesterday, we are going eventually to discuss Ohm's law, the equation for a circuit. That's what electrodynamics is all about. The main electrodynamics problem is a circuits problem, where we're going to use Ohm's law voltage equals current times resistance. Now, of course, previously in the static electricity unit, we said voltages work over charge. In yesterday's video, we said that current is equal to the rate at which that charge flows. And so the last thing we need to discuss here for today is the resistance. And what we're going to see is that there is a standalone equation for the resistance in a wire, and that's the main thing we're going to be going over today. And so I'd like you to take this first opportunity here to write this all under the heading electrical resistance. So most basic definition you can give for resistance is that resistance is the opposition to the flow of current in an electrical device or conductor. More resistance means more opposition to the flow, which ultimately means less flow. That's the basic idea. Now, what we should say here also is, because you guys have already taken basic electricity in shop where you talked about circuits, well, we typically think of resistance being introduced into a circuit by resistors, which are really just chunks of carbon that are designed to oppose the flow of current. Basically, just because the electrons that flow through the resistor crash into these big chunks of carbon and they lose some of their energy as heat, and that makes them slow down. All wires have a natural resistance too, which is what we're discussing today. Now, in general, in a circuits problem, you usually don't count the resistance of the wires. And that's because the resistance of the wires, when you compare them to the resistance of the resistors, is really, 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 really tiny. And so if the resistance of the resistors is like 1,000,000 times bigger than the resistance of the wires, you don't really care about the resistance of the wires. It's not really going to change your answer much, maybe by 1 decimal point or something. But that's really it. Or I should say 1 decimal place. Instead of getting 100 for your answer, you'd get like 100.001. Something like that. That's the idea. And so resistance, what you really need to know is that resistance is the opposition of flow to an electrical current. And that exists in traditional devices like motors and blower fans or whatever, in resistors, and in wires. Our main focus today is going to be wires. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, so now we can take the opportunity here to ask what I think is a pretty obvious question at this point. If we're talking about the resistance of a wire, it would probably be a pretty smart idea to ask the question, what determines the resistance of a wire? The answer is pretty straightforward. There are 3 things. The composition of the wire, or in other words, the material the wire is made of, determines its resistance. Certain materials have more resistance, certain ones have less. The length of the wire determines the resistance, and the cross-sectional area of the wire determines its resistance. Now, cross-sectional area is a technical term. For right now, we'll just say the cross-sectional area is how fat or skinny the wire is. That's the basic idea. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now one of the first things we want to talk about here is what the equation looks like. And what I want you to realize is you can figure out just by thinking what the equation is going to look like. Because you've experienced situations where you yourself are flowing through something like a conductor. Think about the hallways at Aviation High School, at least for those of you who aren't freshmen, which is basically all of you. You have spent time in the building at Aviation High School during normal times where there are 2,400 kids in the building or however many it may be. And it's hard to get through the hallways. And the situation is perfectly analogous to how electrons flow through a conductor. Remember, if we're talking about the resistance being larger, it means it's harder for electrons to flow from one end to another. So let's say you're trying to get through the hallway at school, and you're trying to get from point A to point B. And instead of making the hallway this long, where point B would be right here at the end of this line where I have it drawn right now, let's say we made the hallway longer. And instead of making point B here, we made point B all the way down here where there's so many kids in your way you're trying to get down the hallway. Is it now easier to get down the hallway, or is it harder if it's longer hallway? It's harder. So what we can say here is that if we have more length, then it's harder to flow, and so that means there's more resistance. Now, of course, we could ask the flip side of this question. Instead of traveling from point A to point B at the end of this narrow hallway, what if we made the hallway significantly fatter? If we made the area of the hallway larger? So instead of being like a little narrow hallway like this, we made it a nice big wide open area. Is it now easier or harder to get to the end? Well, if there's more side-to-side space in the hallway, you should realize it's going to be easier. And so if we have more area, then that's going to make it easier for people to flow from A to B. And so there's going to be less resistance. That should make sense. If the electrons have farther to go in a wire, it's harder for them to get from one point to the other. So more length means more resistance. But if the wire is fatter and there's more side-to-side area for the electrons to flow, then more area is going to mean less resistance. And now we can use this information to think about what the equation is going to look like. If more length means more resistance, so more of one thing means more of another, what kind of mathematical relationship is that? Well, if more of one thing means more of the other thing, then that means the resistance is going to be directly proportional to the length. And so we should see the length then in the numerator of the equation. What about the area? More area means less resistance. So if we have more resistance, what does that tell us about the area? Well, that means we would have less area. What kind of mathematical relationship is that? That's an inverse relationship. And that tells us we should expect to see the area in the denominator of the equation. And doing this basic thought experiment, we can then use to sort of try to make up what the equation is going to look like. And then we can test that in the lab to see if that equation is correct. And sure enough, that's exactly what scientists did. And they confirmed that this equation that we're about to look at is, in fact, correct. Take a second to pause this video here and write that down. And when you hit play, take a look at the equation. All right, so the equation for the resistance in a current carrying wire should not come as much of a surprise based on what we just said here. The symbol for the resistance in a current carrying wire, as is probably not a surprise to you, is R. The equation looks like this. R is equal to rho, which is a symbol I'm going to define in a minute. That's a Greek letter that we pronounce rho, times the length. Notice the length is in the numerator. That's because they're directly proportional. And then divided by the area, which is in the denominator, of course, again, because those are inversely proportional. So let's be clear about something here first. The first thing we want to define is this value here. This letter is a Greek letter that looks a lot like a P. It is not a P. It's a rho, and it's pronounced R-H-O, rho. This is a Greek letter. And it is defined in this equation as the resistivity. Now, this is a special term for the resistance in a wire. It is a value that is unique to each kind of material. Remember, we said the composition of the wire or the material the wire is made of is going to affect its resistance. That's an important thing to realize. Of course, L, the length of the wire, is going to be important for the resistance too. That's the symbol L is the length of the wire. It's measured in meters. And A is the cross-sectional area. And because it's an area, it's measured in units of meters squared. Now notice in this equation, if rho is measured in units of ohm meters, the symbol for ohm is the Greek letter omega, and then if we have to multiply that by the meter and then divide it by meter squared, it should make sense here that this meter squared is going to cancel both of these meters and leave us behind the unit ohms for the resistance in a wire. This unit ohms is spelled O-H-M-S, named after a physicist with that last name, George Ohm. Of course, this is the same Ohm responsible for Ohm's law. And so I'll just write here, the unit for ohms is the Greek letter omega, and this is an uppercase omega. Notice, I think it was just really coincidence since the dude's name was Ohm, and people were like, oh, there's a Greek letter that has a name that starts with ohm, omega. They just decided to give it this name. Kind of goofy, but that's the idea. Take a second to pause this video here and write that down, and when you hit play, we'll move on. I just realized here I wrote upper omega. That should say uppercase omega. And that's the basic idea for that. Now, there are a couple of things I want to discuss here before we move on to actually solve problems. The first is what the cross-sectional area actually is. Now, as I said, we can use cross-sectional area basically, like we can say how fat the wire is, and that's close enough. But I want to just actually show you this picture. If we're talking about a wire, which in almost all cases in this class is going to be a cylinder, it's going to be a cylindrical wire. What we mean when we say cross-sectional area is if you take the wire and you cut it, and then you look at it from the side you just cut, what you're going to see is a circle. So when we say we're taking a cross-section of something, we basically cut it, and then we look at the side we just cut. Think about a sandwich. If you took a sandwich and you cut it in half, and then you looked at the side of the sandwich, and then you saw your two pieces of bread, all your meat and cheese and stuff in here, that's a cross-section of the sandwich. And so if we take the wire and we look at it head on like this, we would see a circle. And so the basic idea here is the area of this circle, which is pi r squared, is going to be the cross-sectional area. Now, let's be clear. In almost all cases in this class, you're not going to have to calculate the cross-sectional area. They're just going to tell you. But since all wires that we'll be dealing with are cylinders, the cross-section will have the area of a circle, which is given by the equation pi r squared. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on. Now, as I said, this equation also has the Greek letter rho in it, which stands for the resistivity, which is a value unique to each material. If you go to page 4 of your reference table, you will see a chart. That chart is titled Resistivities at 20 degrees Celsius. Just so you know, and of course you could look this up, I forget exactly what the number is, but resistivity at 20 degrees Celsius is about room temperature. I think it's like 68 degrees or something. It's like very close to room temperature. They wanted to make it a nice round number, so they called it 20. Room temperature we typically think of as like 70-ish degrees. And so notice they list the resistivity for all of these different materials: aluminum, copper, gold, nichrome, silver, and tungsten. These are all just different kinds of metals. And so depending on which metal you're given in the problem, you're going to go to the table and use that value for the resistivity. Now, one thing that should be pointed out, for some stupid reason, they wanted to keep all of the resistivities in this table with the exponent times 10 to the negative 8. And so they actually wrote nichrome's resistivity in incorrect scientific notation in this chart. You should realize that 150 times 10 to the negative 8 is the same thing as 1.50 times 10 to the negative 6 ohm meters. Now, of course, if it says nichrome, you could just go ahead and use that value and write it as 150 times 10 to the negative 8, but that's something you should just be aware of. Also, notice here, the unit for the resistivities is listed at the top. What I almost always see in this class is kids go to this table, they write down the number, they don't see the unit right next to it in the chart, and so they forget to write it down. Please remember, it is at the top. Now, the last thing I want to say before we go ahead and solve a problem is that the symbol in this course for the resistivity is a Greek letter rho. When you see me write this in a problem, you're going to see me write it like that, or like something like this. And that does not look how it looks in the reference table. And the reason why I bring this up is because I just want to be clear. If you Google rho and then you look at images, you're going to see it looking all sorts of different ways that's not exactly how it looks in the reference table. I usually make it a little more slanty like that so that I don't confuse it with an upper or lowercase p. Remember, a lowercase p is the symbol for momentum and an uppercase p is the symbol for power. And so I will almost always write it with that little slant off at the end to distinguish it from those two terms and make it look something like that. All right, having said that, let's take a look at a problem. All right, so here's the first problem we're going to take a look at. This problem is in the circuits packet, page 5, number 26. It says, what is the resistance at 20 degrees Celsius of a 2.0 meter length of tungsten wire with a cross-sectional area of 7.9 times 10 to the negative 7 meters squared? Now, I think it's important for everybody to realize here, notice, they're specifically telling you the temperature of the wire is 20 degrees Celsius to sort of give you an obvious hint that you have to look at that table in the reference table to get the resistivity. Now, notice here, they tell you this wire is made of tungsten. Tungsten is a particular kind of metal. I believe the atomic symbol in the periodic table of elements is W, and it is a metal that is actually usually used in light bulbs. If you see an incandescent light bulb with a filament in it, it most likely is made of tungsten. That's just a little fun fact for today. So if you take a look at the reference table here, you'll see tungsten at the very bottom, and the resistivity of tungsten is 5.60 times 10 to the negative 8 ohm meters. You got to remember to write that unit here. So we have our resistivity for this problem, because they tell us this thing is made of tungsten, is 5.60 times 10 to the negative 8. And we got to remember that unit, ohm meters. That's a terrible looking ohm symbol. The length of the wire, they tell us, is 2.0 meters. And they tell us the cross-sectional area of the wire is 7.9 times 10 to the negative 7 meters squared. So we have 7.9 times 10 to the negative 7 meters squared. Right? 7.9, 10 to the negative 7. Boom, we're in business. And we're looking for the resistance. So now we have everything to plug in. This is a pretty straightforward plug-in problem here. And so we say R is equal to rho L over A. That's what the reference table says. And so we take the resistivity, which we found from the reference tables, 5.60 times 10 to the negative 8 ohm meters. We're going to multiply that by the length of the wire, 2.0 meters. And then we're going to divide that by the cross-sectional area, 7.9 times 10 to the negative 7 meters squared. Notice the square is on the inside of the parentheses here because the unit is just meter squared. And when you do that math, making sure you put these numbers in scientific notation, and I mean in your calculator in parentheses, because they're in scientific notation, you end up with an answer of 0.142 ohms, which is equal to 1.4 times 10 to the negative 1 ohms, which, notice in your list of answer choices, makes this answer choice 2. Take a second to pause this video here and write this down. And when you hit play, we'll take a look at another example. All right, so that's basically it for this equation. These problems are going to be pretty straightforward plugins. It's going to say, like, what's the resistance? What is the length? What is the area? And they're going to give you all the numbers. I think for the last example of this that I want to look at while we're, in the middle of this video is probably what I would consider to be the trickiest example of one of these kind of problems. Because this problem says a wire has a resistance. The resistance is 1.15 times 10 to the negative 1 ohms. Notice the resistance of a wire is small. The length is 10 meters and the cross-sectional area is 1.50 times 10 to the negative 6 meters squared. The question says, what type of metal is the wire made out of? Huh? All right, well, let's just go ahead and write down the knowns here. They tell us R is 1.15 times 10 to the negative 1 ohms. They tell us the length of the wire is 10.0 meters, and they tell us the cross-sectional area is 1.50 times 10 to the negative 6 meters squared. The obvious question here is, well, what are we missing? We're missing the resistivity of the wire. That's what this question is asking us. When they say what type of metal is the wire made out of, what we said earlier is that the resistivity is unique to each individual metal. And so we solve for the resistivity value, and then we use the table to try to match it up and see if we can figure out what kind of metal it is. So let's go ahead and solve for the resistivity here. Well, the first thing we're going to have to do is write the equation from the reference table, R equals rho L over A. And if we want to solve that for rho, well, the first thing we got to do is multiply both sides by A, right? So we have rho L equals RA. And then notice we just have to divide both sides by L. Now we're in business. We have an equation for rho. Rho is RA over L. So rho, the resistivity, is 1.15 times 10 to the negative 1 ohms times the cross-sectional area, 1.50 times 10 to the negative 6 meters squared. And then we're going to divide that by the length of the wire, which is just 10 meters. When you do that math, making sure you have all your numbers plugged into your calculator in parentheses because they're in scientific notation, you end up getting an answer for your rho, or your resistivity, as 1.725 times 10 to the negative 8. And then notice here, this meter cancels one of those meters, so our units left over are ohm meters. And that is what the resistivity unit is. So cool, we're good. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at the resistivity chart so we can match this up to a metal. Because notice that's what the question asked. It said, what is the metal? All right, so if we go to our reference table chart here, we're looking for 1.725 times 10 to the negative 8, 1.725, and there we have it. This wire is made out of copper. Now, I want to be clear about one thing. I made this problem up. I didn't go too nuts about making sure it exactly rounded to 1.72 times 10 to the negative 8. It ended up being 1.725, and that's fine. Because notice the question says the wire is made out of a particular material, but it doesn't say anything about it being 20 degrees Celsius. So it's important to realize here for these kind of problems, when it is a problem that is written by the regents, it is going to exactly match one of those values in the reference table. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now very quickly before we go here, we're going to take a moment to discuss two more things about resistance. The first is about graphs. They love to ask questions like this. What is the resistance in a wire, and how does it compare to its length? And how does the graph of resistance versus cross-sectional area look like? We've been talking about this for a while. The shape of the graph is based on the relationship in the equation. According to that equation, since L is in the since L is in the numerator, R is directly proportional to the length. That means on the graph, we're going to see a nice straight line. Of course, on the other hand, because the area is in the denominator, the resistance is inversely proportional to the cross-sectional area. And that means the graph is going to look like this. You should be prepared for these questions because you are going to see them. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, the last thing I want to discuss here in today's video very quickly is resistance and temperature. And we're just going to make a couple of quick notes about this. When a wire is maintained at a higher temperature, the molecules in the wire will vibrate with a larger kinetic energy and thus a larger speed. Remember, temperature is a measurement of the average kinetic energy of molecules. When something is hotter, all that means is the material has its molecules vibrating more. Now, what the hell does that have to do with the resistance of a wire? Well, when the molecules in a wire are vibrating more, they resist the flow of electrons more because they're going to crash into the electrons more because they're bouncing around. And that decreases the current. And if the current is lessened, the only explanation for that is the resistance must have increased. So when the temperature increases, the resistance of a wire increases. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And so a good animation of this effect is going to look something like this. When the wire is cold, notice the red dots here, which are showing like the molecules of the wire themselves, they're not really moving around much. The electrons don't really have to, exert much effort to get by. They basically just have to avoid the obstacle. However, when the wire is warm and the material is jiggling all around, it's much harder for the electrons to get through. And that's why when the temperature increases, the resistance increases as well. Now, if you are paying attention in shop, some of you might be thinking, wait a second, isn't that the opposite of what they told us in shop? You have to be careful whether you're talking about a wire or whether you're talking about something like a NiCad battery. If you're talking about a battery, it's a totally different principle. The way a battery works is totally different from the way a wire works. So this is only for wires, not for batteries. Now, to put this in the form of a note here, we'll just say, big note, resistance and temperature are directly proportional. Higher temperature, higher resistance. Lower temperature, lower resistance. That's the idea. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And with that, that's it for today. Remember, your conservation of energy test is tomorrow, and so this will be the last video on circuits before we take the test. But with that, that is it for today. Have a good one, everybody.